Good day, students. Myself, Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. In my enlightening session of MSc Final Physics, I am dealing with fifth paper, that is Solid State Physics. We have discussed various class of magnetic materials in my previous lectures. So, today we will discuss ferromagnetism. What are ferromagnetic materials? Ferromagnetic materials are the materials which have spontaneous magnetization even in the absence of any external applied field. That means if we have a material and we do not apply any field on it, then still it will have a magnetic property, and this magnetization is termed as spontaneous magnetization, and this results in a ferromagnetic behavior in a material. Examples of ferromagnetic materials are pure iron, the well-known example, cobalt, nickel, transition metal alloys. These materials are ferromagnetic in nature. The ferromagnetism is because of electron spin arrangement present in this type of material. For example, here this is the spin arrangement of ferromagnetic material. Here all the spins are parallel, which results in a net magnetic moment. This is the spin arrangement of antiferromagnetic material. The number of parallel spins in this case is equal to number of anti-parallel spin. Similarly, the spin arrangement in ferrimagnet and antiferromagnet material is shown. In our previous lectures, we have discussed superconductivity. We know that superconductors are the materials which have zero resistivity, or we can say infinite conductivity, when the temperature of material is less than a particular temperature termed as critical temperature. At Tc, material transform from normal to superconductor. Similar case exists in ferromagnetic material. The ferromagnetic property disappear above a temperature termed as Curie temperature. Above this, the material will be paramagnetic. Just similar to superconductors, above Tc, the material is normal, and below Tc, material is superconductor. Similar behavior is here. Above Tc, that is Curie temperature, the material will be paramagnetic, and below which the material will be ferromagnetic in nature. Now, since these materials have itself magnetization, and that magnetization is termed as spontaneous magnetization. This magnetization is temperature dependent phenomena. The variation of magnetization Ms with temperature is shown in graph. Temperature is shown here on x-axis, and spontaneous magnetization denoted by Ms is plotted on y-axis. We can see from this graph that when temperature is 0, magnetization is maximum, and in this graph the magnetization is denoted by Ms0. And as the temperature increases, we can see from the graph that magnetization, which is termed as saturation magnetization, it comes to 0 at T equal to Tc. This Tc is termed as Curie temperature. Above this Curie temperature, susceptibility follow the Curie-Weiss law, because as I have already stated, above this the material will become paramagnetic in nature, and the Curie-Weiss law is chi equal to C upon T minus Tc. Here chi is the susceptibility, C being the Curie constant, C is at a particular temperature T, and Tc is Curie temperature. So, a ferromagnetic material has a magnetization which is termed as spontaneous magnetization, and they follow Curie-Weiss law. And the other property is that in these materials we can divide a material into small region called domain, and these domains are spontaneously magnetized. Now I am moving over to the another topic, which is Weiss theory of ferromagnetism. According to Weiss theory, we have a ferromagnetic specimen and we divide this into small regions, and these small regions are termed as domains. And these individual domains, they are spontaneously magnetized, and we have to determine the magnetic moment of our ferromagnetic specimen. For this, what we have to do, we have to take a vector sum of magnetic moment of individual domain. So, the main hypothesis of Weiss field theory is to divide a material into small region termed as domains. Now, the second hypothesis of this theory was that within each domain there is a spontaneous magnetization. The cause of this spontaneous magnetization is the existence of molecular field. This molecular field is denoted by Hm, and this molecular field is proportional to the magnetization. That means Hm is proportional to M. Removing the proportionality sign, we have a constant Hm is equal to lambda m. This lambda is termed as Weiss field constant, and it is independent of temperature. So, for a material, the effective field will be, it will be the sum of external field capital H and the molecular field Hm, which has a value lambda m. Therefore, H effective will be H plus lambda m. Now, I have a ferromagnetic solid which consists of n number of atoms per unit volume, and each atom has a total angular momentum quantum number J. And for this, the magnetization will be M equal to Ng mu B J Ba. Here Ba is the Brillouin function. It has a value denoted by the expression 2j plus 1 upon 2j cot hyperbolic 2j plus 1 upon 2j A minus 1 upon 2j cot hyperbolic A upon 2j. Parameter A has a value G mu B J upon KBT H effective. On putting the value of H effective to be H plus lambda m. Here G is the Linde G factor, mu B is Bohr magneton, J is total quantum number, M is the magnetization, and lambda is the Weiss field constant. Now since we are dealing with the ferromagnetic material, this ferromagnetic material is magnetized itself. So there is no need of any external field. Here H is the external field. Hence for a ferromagnetic material we are taking H to be 0. So putting H to be 0, we get the value of A equal to G mu B J upon KBT lambda M. Here I am writing, in spite of M as a function of T. This is written to show that magnetization is a temperature dependent phenomena. So I have obtained the value of A. The saturation magnetization at 0 Kelvin, we have shown that it is maximum and it has a value ms0 equal to Ng mu B J. Now I am dividing the value of Mt obtained by this expression and ms0. Using these two expressions, I get this expression. The ratio of Mt upon ms0 is kBTA upon n lambda G square mu B square J square. And dividing this expression, which we have written earlier, m by ms0, I get the value BA. So these are the two equations of magnetization where we have obtained the ratio of magnetization at a temperature T and magnetization at absolute 0. Now I have to obtain the solution of these two expressions. The method used is a graphical method. I am plotting these two expressions simultaneously. So here I can see that my first expression is temperature dependent. The second expression is independent of temperature. I am plotting the curve for 3 temperature range. The first temperature range is above Tc, second being at T equal to Tc, and third is for T less than Tc. Here Tc means Curie temperature. Since this expression is independent of temperature, I will get only one curve. So I am plotting m upon ms0 as a function of A. This is the plot of m upon ms, which is equal to B. Now there are different plots for different temperature range if I plot this expression with A. These are the 3 curves which are for 3 different temperature range. From this graph it is clear that for T equal to Tc, the straight line, it cuts the Brillouin function at origin, that means at this point, and the another point at which these two graphs intersect is this. The intersection at A equal to 0 is unstable non-equilibrium condition, and the other two curves, they do not interact with the graph of Brillouin function. That means we have obtained the solution of the two expressions by graphical method. The point of intersection shows that the magnetization exists only when temperature is less than Tc. And this magnetization exists even in the absence of any external magnetic field. And for T equal to Tc and T greater than Tc, there are no intersection point of the two curves. Thus, we can conclude that a ferromagnetic material has an existence only when temperature is less than Tc, and existence is possible even in the absence of any external applied field. That means at or above the critical temperature, which is Curie temperature, there is no magnetization. That means ferromagnetism exists for temperature range T less than Tc. So students, today we have discussed an important point, that is Weiss theory. I am summarizing what I discussed today. Weiss theory is based on basically two hypotheses. First is to divide a specimen into small regions called domain, and each domain is spontaneously magnetized, and the magnetic moment of the material will be obtained by vector sum of magnetic moment of individual domain. And the second hypothesis is that there is a molecular field, and this molecular field is given by Hm is equal to lambda m. Here lambda is Weiss field constant and m is the magnetization. And from this theory we have proved that ferromagnetism has an existence only when temperature is less than critical temperature, and this critical temperature is termed as Curie temperature, and ferromagnetic material has magnetization even in the absence of any external magnetic field. Thank you students for watching.